we've got a little bit left to finish up in talking about reactions in aqueous solutions, specifically finishing up our talk about oxidation numbers. We can see a couple of examples here of redox reactions where the oxidation number of iron is very clearly changing. We start out here with iron. So this is iron metal. This is a solid at room temperature, nice silvery solid. But when it's left exposed to oxygen, both of which have a 0 oxidation number based on the rules that we discussed earlier, they'll react with one another and form what we usually call rust, brownish, porous material that we find on the outside of a lot of old Chevys. And so iron becomes a 3+ ion as oxygen becomes a 2- ion. Oxygen was reduced from 0 to 2-. Iron was oxidized from 0 to 3+. Now if we find iron in the ground, quite often we'll find iron ore in this same condition, iron oxide, or what we would call iron 3 oxide to give it its systematic name. We can, under the correct conditions, reduce that iron back to pure iron and get iron back using carbon, and as our product we would be generating CO2. Now what happens here is the iron goes from 3+ to 0. That's easy to see. The oxygen is 2-. The oxygen is not going to change. It's going to stay part of the compound and go to 2-. And whenever oxygen is part of a compound where the compound's name doesn't have peroxide in it and there's no fluorine in the compound, then the oxygen is always going to be 2-, or have a -2 oxidation number. And that includes covalent compounds like CO2. So if the oxygen is -2 and there are 2 of them, that adds up to -4. If there's only 1 carbon, in order to have the sum of the oxidation numbers on our compound add up to 0, the carbon must be +4. And this is going to be the case when we're looking at the oxidation numbers on a neutral compound. They need to add up to 0. When we're looking at the oxidation numbers of the atoms in a polyatomic ion, those oxidation numbers need to add up to the charge on the ion. So we'll try out a few more of these in class and on the homework. Now in order for us to tell if a redox reaction is going to happen, particularly a redox reaction involving a metal, it'll be helpful for us to have some exposure to or understanding of the activity series of the elements. It's a list of elements, and their ordering in the list is based on which are most reactive, which are most likely or stable as ions, compared to which are most unreactive, which are most likely to find or most stable as metals. Copper and silver and gold tend to be on the unreactive side. So if we make a copper nitrate solution or copper sulfate solution like we have here, copper's unreactive. It's in this solution as copper 2+ ion, but it would rather be copper metal. Iron, on the other hand, is a bit more reactive. It's on the reactive side of the series. And so if we dip iron into that solution, the iron and the copper will change places. The iron metal will give a pair of electrons to the copper ions, become ions in solution, and then those copper ions will coat that piece of iron and take over the spots where the iron were, and you get a copper coating. On the other hand, copper, even though it's on the non-reactive end of the list, is more reactive than silver or gold. So if we have a silver solution and we dip copper into it, the copper will go from being metal with a 0 oxidation number to being ions in solution. That's why the solution is turning blue. And the silver will come out and coat where the copper wire had been. So I don't want you to memorize this. This is in your textbook. I got this picture from a different version of the textbook, so it says chapter 7 here. But you'll find it in chapter 4 of your textbook. Don't memorize it. If it's necessary to answer a question on a test, then it'll be given to you. We'll use this a little bit, this semester, and we'll use a numerical version of it a lot more late next semester when we do redox reactions in terms of electrochemistry. But we rate these as whether they're more stable than hydrogen molecule compared to hydrogen ion. The ones that are more stable are copper, silver, mercury, platinum, and gold is the most stable that we find on this list. That means that gold will always come out of solution when it's placed in contact with another metal. The most reactive, the most likely to find as ions, are the ones at the top of this list: lithium, potassium, barium, calcium, sodium, all the metals on the left-hand side of the periodic table. As we work our way down, we get to atoms that are less and less reactive. Aluminum, manganese, still fairly reactive, but not as much as these. Zinc, chromium, iron, cobalt, nickel, and tin are kind of in between. Notice we see nickel and tin used in certain applications, tin cans, nickel coins, where we want rust to happen slowly or not at all. But copper and silver will corrode or oxidize even more slowly and to a lesser extent than these metals. So that's the activity series of metals, and this is mostly the more common metals. It's not all the metals in the periodic table, but the ones that would be used in industry and in chemical practice most often are on this list. Right here, you can pause the video and write these down. These are the problems that I suggest you take a look at and try to work through some of them before the next class period, next couple times that we meet, and see how you do with these, and prepare to ask questions on any of these that you have questions about. We'll work through the example problems I mentioned in the video, as well as some of these as we have time before we do our next quiz. And enjoy your chemistry work.